Okay. Welcome to. Do I have a deodorant problem? Why is there nobody sitting in the front rows here and everybody's in the back of the room everywhere else? I have to get new deodorant. All right. Yeah. So last time we finished, this is the steam turbine. That's what 85 megawatts looks like. A lot of plants. This is like a small one. A lot of plants will be like 1,000 megawatts or 500 megawatts. So, 6 of these or a bigger one. This plant, by the way, I think I mentioned my senior project partner was the manager for this plant, and that's why I got the photo when they're swapping it out. They had one turbine, I believe. Interesting thing about it is it's in Pennsylvania, near coal fields, and they sited the plant near a slag pile. Like when they were mining the coal, they bring out the coal with a bunch of rocks, and the rocks had some coal, but it wasn't commercially saleable. So they just put it in the rocks to this way and the saleable coal that way. But there's a bunch of coal mixed up within it. They had a boiler that was designed to burn rocks. They would actually take the rocks and sort of smash them, and there'd be like little seams of coal in there, and it would burn the coal out from among the rocks, and then they'd have the ash that came out was rocks with the burned ash. But they were actually like reprocessing that coal field. It's a small plant because they wanted it to last for 20 years because for the amount of effort you put into building the building and everything. So they had to size the plant so that it was the pile of rocks there was a 20-year supply for the plant. So they figured out how much that it was a big pile of rocks, but they basically just worked their way through the pile of rocks with a relatively small power plant. But it's not exactly renewable energy, but it was using already mined coal that was mixed within rocks and wasn't commercial to sell to somebody. You really don't want to buy a pile of rocks. Like, if you order a cord of wood, you don't want half of it to be like rocks. So anyway, that was designed to do that. So it's smaller as a result. So let's go through one of these. I'm going to come back to I haven't had a chance to work through the examples on the air standard cycle tomorrow. That'll be what we do, auto cycle example, so you can see what that goes on for homework. But since we already did this process in the homework, we're going to tie it together with an entire cycle. So let's see how that works. TS diagram. The reason we like the S diagram is when you have an isentropic process, we can show it as a straight line. Graphically, it helps us think about how things are happening. But what goes on, you get, and I'm going to use number things differently than they do. I'm going to say number 1 is the highest energy state, and then go around that way. They're doing number 1 as the lowest energy state, which is sort of consistent with how they've been doing the air standard cycles. But since our test, we did this with 0.1 and that was 0.2. And in this case, we have 75 kilopascal. Basically, there is always a low pressure side and a high pressure side. And then you have the temperatures, depending on how much energy. The energy comes in the boiler. You have to condense it here, and I always wonder why don't you just like pump the steam and save some energy? Don't lose that energy, just pump it up. It turns out it takes so much energy to pump something that's a gas. It actually is cheaper to get the energy out and then just pump a solid liquid, because the liquids are a solid thing you can push. In gas turbine, which you're pressurizing a vapor or a gas, ideal gas. You know, it can be a third or easily a quarter, third, even a half of the turbine energy goes into driving the compressor to compress things. In this case, it's going to be more like 3% of the turbine output. So this waste heat we need to get rid of so we can do that. So, there's basically three things that we know, and I'll circle them on here. Again, I'm making a table. A table helps me know what is it I already know and what is it I need to find out. It helps organize your task. So what I know is at point 1, I got 3 megapascals. My temperature is 350 centigrade. And that's a given, so I'll circle it to remind myself. What else do we know? So this is 3 megapascals. By the way, on this temperature entropy, temperature is a constant. The pressure lines kind of do swoop up like that, but if they cut through the saturation dome, the temperature is going to stay constant as it's changing phase, so it cuts and then goes sort of horizontal because of that boiling thing. So that's how that looks on the diagram. What else do we know? The pressure starts at 3 megapascals, and on this side it's 75 kilopascals. So at state 2, we got state 2s and state 2 actual. We're not going to deal with the actual one yet. State 2s says this is the limit. This is how much energy is availably converted because the entropy value stays the same. In an ideal process, it can only stay the same in a perfect world, or it increases in the real world. So entropy stays the same. That's the best we can do. So that'll be my state 2s. But in state 2, it's 75 kilopascals. Where else would it be 75 kilopascals? Yeah, state 3, it's still, the condenser's still at 75 kilopascals. And the state 2 actual, if we get to that, that's still, I mean, the pressure is what's real. And at state 4, is it still 75 kilopascals, outlet to the pump? It might be maybe the new pressure. The pump creates the pressure, the boiler creates the temperature, and pressure and temperature together. So, yeah, so it's going to be 3.0 megapascal. And let me fill in a few other things. If we're in saturation, definitely state 2 and 3 are going to be at saturation temperature. Now, we won't know for sure if we're in saturation until we look at tables to see if the entropy falls down at that temperature, or at that pressure, what the entropy value is. If the entropy falls between the two values for at that pressure, then if we know we're in saturation. If we're in saturation, we know what the temperature is right away. Don't really care what the temperature is, but that's what it'll be. So let's put in states. What do we know for sure? The state here is super heat. Yeah. And what do we know for sure on state 3? Yeah, it's going to be saturated liquid. And you could say X equals 0 in saturation. That means 0% of its vapor. And what do we know at state 4? Same stuff, and now we pressurized it. So that's going to be compressed liquid. Don't know for sure about these until we get some data. I know this is going to be my temperature, saturation temperature. Don't know for sure if state 2 is going to be saturation. I bet it is, but we'll check that. But this is definitely going to be saturation temperature because it's saturated liquid. We just condensed it. So some of these things we're going to be able to fill right in on tables. Start with the superheat. Superheated water, and we want three megapascals, and at 3 megapascals, saturation temperature, the boiling temperature would be 233.85 degrees centigrade. We're at 350, so that confirms what we already knew. 350 degrees. There's all these numbers. What am I going to do with all those numbers? At the top of the page, this is specific volume. This is internal energy. This is enthalpy, which is really what we care about. And this is entropy. Entropy is going to help us find the state 2 enthalpy. It's the only way we can really find it, because they have the same entropy value. So these two numbers are the ones that I'm interested in. That's how much energy is in the steam, and this is the entropy value for it. We're going to go look on the saturation table for something that has something like that value. So I got a 6 point, what is it?
7.50.
Thank you. And a 31 something or other.
16.1.
And those are kilojoules per kilogram for the H. Kilojoules per kilogram Kelvin for S. Now let's go back and under the pressure table. Look for 75 kilopascals. First thing is the S2S equals S1. It's isentropic. That's how we're defining that point. So we come across here and we find these values. Here's the entropy value for liquid. Here's the entropy value for vapor. And this is just subtracting the two from each other to save you some time. They could delete this table and you wouldn't lose any information. It's just, I had a test for somebody, a couple tests, people were using this number and subtracting it from one of these, and that's too much work, and it was an error. Is our value between these two? So if it's between these two, that means, yes, we're in saturation, life is good. So now we know what the temperature is. We don't know the enthalpy value. We use these two numbers now to figure out what the quality is. And then we can use the quality with these two numbers to find out what the enthalpy value is for the perfect state. And we now know we're at 91.76 degrees. So my actual values. Or maybe I should write this as a formula. And I'm doing too much with this actual thing. I'm going to say that my S2 S minus SF over SG minus SF. So 6.7450, we found that from our superheat state. And in the perfect world, entropy stays the same or increases. Perfect world is 0. And then my value for this, let's see, 1.2132. And on the bottom it was 7.4558. And these are all units of kilojoules per kilogram Kelvin, but they cancel. So what? Anyone have happy fingers on that one?
0.886.
0.8. Do we have more digits on that?
1. L886.
61. Another one?
4.
Okay. Since I've got 5 digits here, I'm going to keep my 5-digit precision. And this also happens to equal my H2S minus HF over HG minus HF. It also equals the values for a specific volume. All those things. So if I solve this one for my H2S, let's see, equals HF plus XH. And I'll say HFG now. I'll use that center column. So again, at this, got HF is 384.44 plus 0.88614 8. F minus G is 2278.0 kilojoules per kilogram. Is that making sense, what we're doing there? The only way we know what the pressure is going to be. We don't know what quality is going to be. The only point of reference we have is that in the perfect world, entropy wouldn't change, so we have isentropic. So we take the entropy value above, take it down to the new pressure, and figure out where we are on that, at that pressure. Could have been superheated, usually isn't. So AH, something like 2400.
2403.1.
So that is 2403.1. Perfect. And now we know we have a quality of 0.88614. State 3, saturated liquid. I don't even care what the entropy is. I don't need it. I only need, really the only place, I mean, I could come up with a value for it. It's possible to do that, but the only time you need it is in this turbine process. It's the only way we can find state 2S. So I just don't even care about that. So I'm just gonna mark it out. But it turns out to be easy to find. It's saturated liquid. And the saturated liquid happens to have the value of HF, which is 384.44. So,
Kind of run them off to the side.
Thank you. So, for the simple cycle, I'm not going to deal with the actual states yet. We'll come back to that. State 4S. Now what? Goes through a pump.
So it's the same temperature?
Yeah. So how much?
Pressure?
It's going to. That's one of the things that when you pump it, in a perfect world, there would be no losses. There would be 100% efficient, and all the energy you put into the shaft of the pump becomes fluid energy. And that's what we calculate when we say changing pressure times volume flow rate is power, or volume flow rate is power. If you just do pressure times volume, it's work. And we're going for work here and work per kilogram, because then if we do kilograms per second, you get work per second, that's power. We can scale it up and down if we do it per kilogram, and then we can solve for a flow rate for, 1 gigawatt or whatever we want. But the difference between here and here now, it's a thermodynamic process, it's a fluid process. We just have to calculate it. But what do we use for volume? Pressure times volume. We don't have volume flow rate, but we're not looking for power, we're looking for work. We just need volume. Is there some place where we have something, maybe we get a volume per kilogram? It's our specific volume, same line. So let's see what that looks like. Now we can use this. This is where specific volume becomes really handy. Right about here, for the saturated liquid, the volume is 001037, and that's meters cubed per kilogram. Well, if you turn this upside down, you're talking about 1,000 kilograms per meter, off by 3%. But that's, I'm going to take, let's see, I better do this on another sheet. Work 3 to, and this is, that calculation is an isentropic one in that it's not really about the entropy as much. If it's 100% efficient, that's as good as it can be. It's not a heat engine, so you really don't, it's just a pump. And when it goes, the amount of thermodynamic work that's done is that pressure times volume thing. If you add an actual pump, it would have an efficiency. You'd have to put more energy into it. There's friction, and the friction generates heat. There's fluid friction. If you're causing turbulence, the fluid's rubbing against itself, and that generates some heat. So you'd have losses, and they would cause the water to warm up. And you can actually just like take something and stir a bunch of water and leave it in there and keep stirring it, and the water will get warmer. But the water, it's not a very effective way to heat up water. I guess that's what I can say about that. So, my specific volume here was 0.001037 meters cubed per kilogram. Let's see how we can turn this into enthalpy. So delta P, it's at 3.0 times 10 to the 6th. That's my mega, and pascals is Newton per square meter. minus 75 newtons per square meter. Oops, 75 kilo. So, times 0.001037 meters cubed per kilogram. And two of these meters are going to knock off two of those, and you get Newton meters per kilogram. And we're going to get a number. $2,000. Oh well, get happy fingers gone here. Let's do about 75. 3,000 minus 75 times 10 plus 4 or 1 times 4%. 29.75. That's my prediction. 2033? 3033? I'll be darned. Newton meters per kilogram, but wait. 1,000 Newton meters is 1 kilojoule. That's the kilo is the 1,000, and a Newton meter is a joule. So that means we've got 3.03 kilojoules per kilogram. That's the amount of, the least amount of work, the amount of work that goes into the fluid from the pump. If the pump's 100% efficient, that's how much work it did. So, if we've got 3.03, now let's go back to our table. Before it went into the pump, the enthalpy was 384.44. We just added some work to it. An enthalpy is internal energy plus work. We just did work, so we can add it to there, and it's just going to take this number up another 3.03. So and the things that I actually screwed this up when I first started teaching this. The specific volume is like, I don't know what volume is. Well, it's use the specific volume for the water you're pumping, and that is water, saturated water with this condition. That's how dense it is. So you want to pick the fluid that you're pumping. That's the one that matters. So what did we just say? 380. 7.47. All right. What if the pump was only 50% efficient? You'd have to put in twice this amount of work. And what would happen to the other, the work beyond the pumping work that you did? It's if the pump, this is if 100% efficient pump, that's how much work gets done. If you had a 50% efficient pump, this is how much work got done, but the amount of work you had to put into it was twice as much. What happened to it? Where did the rest of the work go? Friction and the turbulence that's going to cause, it warms up the water. How warm would it be if this went up, 3 kilojoules per kilogram? I think what's 4.18 kilojoules per kilogram is our C sub P for water. It wouldn't even go up a degree in heat.
That'd be Kelvin?
No, a change in temperature Kelvin is the same as a change in temperature centigrade.
So
It's just there's an offset.
it would be in Celsius or Kelvin.
Yeah, Celsius. To me, the Kelvin really matters if it's ideal gas law and you need absolute. If you just have one number, if you're doing a density of air, it really matters. But if it's just a change in temperature from point A to point B, the difference between them is going to be the same because that offset's going to wash out. So, yeah, it could be a really inefficient pump. And what's the next thing you're going to do to this water? You're going to maybe try and heat it up? Do we really care how efficient the pump is? It's probably more important for the pump to be like run for 20 years without anybody looking at it. You know, reliability is going to be more important on the pump than efficiency. Because all the wasted energy is just energy you don't have to put into the boiler, and it's going to be insignificant energy. So turbine, the efficiency of the whole system is going to depend on how effective the turbine is. You put all your into the turbine, it's all about how can you make it work better and be more efficient. In the pump, it's how can you make it run for 20 years so that nobody even has to look at it, you don't have to pay for maintenance and so forth. Yeah. So based on, now we have tables, what is the net work? The work out now is, you know, I can start filling in some of these numbers. What is the work out going to?
It would be the change in enthalpy between the turbine.
Yeah, and the turbine, if the turbine is 100% efficient, and this is the best case we can do, then we gave it this much energy, it expanded and came out with this much energy. The energy had to go somewhere, so it went into turning the shaft. So that's going to be the difference there. Let's see, H1 minus H2S, and that is, geez, I can almost do that. We've got a 13 and 7. How much heat did we have to put into it? Came out of the pump with an enthalpy of state 4, 387.47, and all we did from there was add energy. The temperature, it warmed up the water until the water boiled. It boiled the water, changed, phase change, and then it heated it up some more above that to this value. And if you take the difference between these two, that should give you the Q in. So that's, I'll say H1 minus H4S in this case. So what is that? Two 2728 point something? 0.6. And yeah, basically so the net work being done is 713 minus 3. And that 0.03, we calculated that, but it kind of washes out. So it's like 710 kilojoules per kilogram. Q in, that's what we paid for. is 2728.6. And cycle efficiency for this operating point,
Like, can you bring it down?
oops, yeah, there we go, is net work, this is the pump, turbine, divided by Qn, and that is 710 divided by 2728. I'll give it all those digits, but
Don't we add 3 too?
no.
No?
We already took the 3 away here. This
Oh.
is the net work, because the 3 was subtracting because you had to turn the pump.
Oh, we're using the turbine to turn the pump.
Well, you don't really use the turbine to turn the pump, but you might use the turbine to turn a generator, and the generator powers the pump, and that's part of the load on the turbine turning the generator.
So you get 26%.
Give me 3 digits on that one.
26.2602.
Yeah, good enough. 0.260. Now that's an efficiency for the entire cycle. So, it's all about, if we fill out these H's, then we can add and subtract them as needed. It's mostly subtracting, dividing. This is how much energy dropped, and this is the base, as far down as you can go because of that entropy thing. We can use it. That's the only way we can find this point. The real turbine wasn't this effective, and this number's going to drop. This is an ideal turbine. How do we figure that one out? That's, if now let's see what happens what if we threw in a isentropic efficiency for the turbine, that's what we did now is how much energy was really available. Say that's 0.90. That means work actual equals 0.90 times the isentropic work, which is really what we had here, the net isentropic work for the turbine. And we decided the turbine was 713. So 90% of, actually I should be doing this on a different page.
90% is 713.
Yeah.
641.7.
641.7?
Yeah.
I'm going to spread this out a little bit. So, and that's what the test had, that data point on it, something like that. So what does that mean? H2 actual is going to be H1 minus basically the work of the turbine actual, which made it 3116.1 minus 641.7, because we weren't able to use all of the 713 kilojoules. We were only able to use 90% of it. So when the output came out, it left some energy on the table, and that output enthalpy will be a little bit higher because we didn't use all the energy. So what's that come to?
$24.74.
And so if we look back up to our table, we can fill that in. I could do the same thing and find out what X is. I could find out what the S is. I really don't care what S is. It's not going to help me. I mean, it's an academic exercise. I could figure it out. But the only time we really use it is for finding that state initially, so we can figure out what 90% of what is. It's 90% efficient, like 90% of what they're good. So that means now if I do my efficiency for the cycle, work at over Qn, same Qn. Yeah, we're done. You get the idea.